The size of a person is something set in stone, decided by the grand lottery of genetics from birth. Nobody can choose to grow an extra inch to reach that top shelf, nor can anyone lose any height when they feel a little cramped. Well, I say nobody, but what I really mean is nobody except Scott Lang, aka the Antman.
Antman can shrink really, really well. It's no longer a case of losing an inch or two in height. Once Antman has finished shrinking, he's not even an inch tall. In fact, he can shrink enough to enter the quantum realm, a realm where everything smaller than an atom resides. This would put his minimum height at smaller than 1 × 10 to the minus 15 metres, which is the radius of a hydrogen atom. So how does he do this?
In the films, the explanation we are given is that the empty space in an atom is simply removed using a magic substance called the Pym particle that exists outside of space and time. Now obviously, we've never found anything even close to resembling this, but let's ignore that for now. What would happen if empty space in an atom simply disappeared?
To answer that question, we need to discuss what the structure of an atom is. The most commonly accepted model in the modern world is the Bohr model of the atom, based on quantum mechanics. We'll get to that eventually, but for now, we'll simplify a little by looking at the nuclear model instead. In this model, an atom is composed of a compact, positively charged nucleus surrounded by orbiting negative electrons. It suggests that the majority of the space in an atom is completely empty, as the nucleus is extremely compact and orbiting electrons are of negligible size.
In fact, in a hydrogen atom, the nucleus only takes up about 7 quadrillionths of the total space, the rest being essentially entirely empty. Removing this empty space by increasing the density to the nuclear saturation density would reduce Scott Lang from being 6 foot as he is in the comics to just 0.03 millimeters tall. Now this is very small, but far from the feats shown in the comics of becoming subatomic.
And even worse than that, it isn't even realistic. The nuclear model has a reason for being mostly empty space, ensuring that the atoms don't explode. There is a force called electromagnetism, which is applied between any two charged objects. Charles Augustin de Coulomb quantified this force with Coulomb's law.
In summary, this means that the force between two charges is a constant multiplied by the product of the charges divided by the separation squared. This means that it is an extremely strong force in close proximity, but the magnitude falls off very quickly as distance increases. So, let's get back to our situation of removing empty space from a hydrogen atom. Two positively charged nuclei will normally have a whole atom diameter between them.
If the atom's diameter is reduced, the force pushing on the nuclei apart starts to increase very rapidly. When all of the empty space in an atom is removed, the separation of charges is now reduced to the radius of the nucleus. Now the repulsive force acting between them is about 231 newtons. This may not sound like a lot, but to put it into perspective, let's calculate the resultant acceleration using Newton's law of F equals ma.
This would give us an acceleration on each atom of 1.3 times 10 to the 31 meters per second squared, increasing its speed by 23 orders of magnitude higher than the speed of light every single second. Now, this acceleration is only at extreme magnitude for a fraction of a nanosecond, as distance of separation reduces the magnitude of force between the two protons very rapidly.
By considering the energy of the system, we can show that in the classical paradigm, each proton reaches a velocity of around 17 million meters a second by equating electrical potential energy to kinetic energy and finding the velocity.
So, quite evidently, placing two protons in such close proximity will result in the material they constitute exploding, so simply removing the space from atoms will not make a person smaller, but instead spread their atoms all over the solar system.
However, before we move on to considering the quantum mechanical Bohr model as a solution for reducing the size of an atom, there is one last classical consideration we must discuss. There are in fact already objects that shrink rapidly at the end of their lifetime. Stars. Once they run out of fuel, the force holding them up against gravity, known as hydrostatic pressure, disappears, so the star begins to collapse.
There is a smaller outward pressure known as degenerate electron pressure, which reduces the speed of this collapse to be over thousands or millions of years. This degenerate pressure simply arises from the cumulative force of high-speed electrons bouncing about and pushing outwards. Two things can occur at the end of this shrinking. The star becomes a supernova or becomes a black hole. Neither of these options are a good thing for a person shrinking.
A supernova is a star exploding, and a black hole is an object with gravity so strong that nothing, not even light, can escape its gravity. Now, obviously, a shrinking person is not going to go supernova, but if they become small enough, they will become black hole. You may have heard it said that once things become dense enough, they collapse into black holes, but if we examine the criteria for black hole collapse, we'll see that this isn't quite the case.
For any object in the universe, there is an associated Forstad radius. This is the radius from the object, within which nothing can escape, not even light. For most things, this is inconsequential, as the radius is within the object itself, so no external object is trapped by its gravity. The formula for this radius is on the screen, where g is a gravitational constant, m is the mass of the object, and c is the speed of light. Rearranging this formula can give us conditions for black hole collapse.
This would mean that a black hole would exist if enough mass was concentrated within a given radius. This may sound like if the density is high enough, but there is a slight nuance, being the shape of the object. For a black hole, the mass must be concentrated within an imaginary sphere within the Schwarzschild radius, regardless of if the object is actually that shape. This is in comparison to density, which is associated with the overall volume of the object and is regardless of shape.
So now we've defined conditions for collapse into a black hole. So how small would a person have to be to collapse? Simply plugging in the numbers, assuming Scott Lang to be 86 kilograms, as he is in the comics, concentrating him with a radius of 6.37 times 10 to the negative 26 meters or less would result in a black hole. Fortunately, this doesn't seem like it will be a limiting factor, so we can move on to reducing the size of atoms using quantum mechanics.
As mentioned before, the most commonly accepted model of the atom is the Bohr model. This involved a compact nucleus surrounded by shells of electrons orbiting at specific energy levels. To understand how this came about, we first need to have a look at Schrödinger's equation.
This is what is known as a partial differential equation. We can see that the function we are solving for, psi, is in terms of two variables, x and t. A partial derivative is the rate of change of the function as one of the variables changes. For example, this first term is the partial derivative of psi with respect to t, meaning it is the change in the value of psi per change in time.
The next term is similar but slightly different, as it is the second derivative, meaning it represents the rate of change of psi. The final term is the wave function psi multiplied by the potential function, which is an interaction of the particle with the system. An important thing to note about this function is that the first term is another way of expressing the energy of the particle multiplied by the wave function.
I keep mentioning psi, the wave function, but what does it really mean? It is a representation of the particle that we are considering. It has a value at every point in space and time, and once the wave function is normalised, the probability of finding the particle at this point is equal to the square of the wave function at that point.
This equation describes every particle but is very difficult to solve. First we input the conditions of the potential and then we can solve for psi. But to make things a little more difficult, there's not just one solution. Every function we can find to solve the equation is known as an eigenstate and can be added to any other solution to find another eigenstate.
So now we have infinite solutions in any situation. The only thing keeping this model realistic is the simple fact that every solution has an associated energy. So even though there are infinitely many possible solutions, all but a select few must have too much energy to be possible in the real world. In an atom, these few solutions that do exist are what determine the energy levels of the shells surrounding a nucleus.
But how does any of this relate to changing size? All of this explanation so far has led us to the available energy levels that the electron can occupy. The next step is simply to relate the found energies to the radius of the orbital shells, making the radius of the highest energy occupied shell the effective radius of our atom. This relation is actually quite simple, equating energy to electric potential from the nucleus and finding the necessary radius.
This gives us the formula on the screen. The first fraction is a constant, and the second fraction is charge on the nucleus multiplied by the charge on the electron divided by the energy. Associated energy levels are always negative, so the radii I find from this formula are positive, which makes physical sense.
Another thing to note is that as energy levels increase, they get closer to zero, meaning they decrease in magnitude. This means that a higher energy level would have a larger orbital radii, and lower energy levels will have smaller. This gives us our next idea for reducing the size of a person, ensuring all electrons are at their lowest possible energy level.
Unfortunately, this is already the case for every particle we currently know of. Electrons fill up the lowest available energy level, meaning there is no room to push them closer to the nucleus. Before we go any further, a quick note on what is meant by available for an energy level. This availability is reliant on a concept called the Pauli exclusion principle.
This states that no two identical fermions can exist in the same state in the same place. A fermion is a category of particle that makes up matter, so the electrons we are considering is an example. For our purposes, this principle means that we cannot put two identical electrons on the same energy level, as orbiting at the same radius is equivalent of existing in the same place, and being at the same energy almost always puts them in the same state.
The only exception comes in when we consider the concept of spin. Every electron has intrinsic angular momentum, despite the fact we consider them as dimensionless points with no axis on which to spin. This is a strange concept, but all we really need to take from it is electrons having angular momentum in opposite directions allows them to exist in different states despite having the same energy. There are two spin states, up and down, so every energy level can contain two electrons.
So where does this leave us in our search for shrinking? Unfortunately, it doesn't seem likely. Our current options are to uncover hidden lower energy levels that for some unknown reasons are not currently occupied, or perhaps discover a new type of spin for electrons to be more packed into energy levels. But as physics currently stands, we are stuck at the height we are.
Well, the prospects aren't looking great for shrinking, but there's two sides to Antman's abilities, and personally, I've always thought that growing was cooler anyway. Who hasn't wanted to stomp through a city like Godzilla, knocking over buildings and tossing around battleships? Or even on the smaller scale, everyone knows someone who'd like to be a few inches taller at the very least. So, how would things work out on this larger scale?
Let's start with the same explanation we had for shrinking, some kind of exotic particle that can change the spacing between atoms. Instead of closing that gap, let's increase it. In a solid, the atoms bonded together are spaced depending on the strength of these bonds. This difference between materials is referred to as their lattice constants.
However, this variance in lattice constants is never more than a handful of angstroms, an angstrom being times 10 to the minus 10 meters. There, of course, are materials in which atoms can have significantly greater separation. Gases can have as much as 10 times the separation between atoms and solids. That said, turning a human into a gas is not exactly conducive to their survival, so this is probably a bad option for our purposes. Not to mention that Antman has the ability to grow vastly beyond a mere 10 times, so even if becoming a cloud of gas was a feasible option, it wouldn't meet our needs.
Truthfully, the idea of increasing the space between atoms in a substance doesn't make much sense to begin with. Chemical bonds between atoms will simply break if pulled far enough apart, and even if it was possible just to inflate the size of an object by increasing atomic spacing, doing so with a human would rapidly lead them to becoming less dense than air and floating into the stratosphere. Meanwhile, Antman behaves as if his mass increases proportionally to his size. Clearly something else is at work here.
So what if we tried that instead? Just add more mass, more atoms, and scale him up like that. From a physics standpoint, this certainly makes more sense than trying to increase atomic separation. After all, thanks to Einstein's mass-energy equivalent, we know that it should be possible to create matter, provided we have sufficient energy. However, therein lies our first problem: sufficient energy.
Einstein's famous equation shows that energy contained in an object's rest mass is an enormous value, equal to the mass multiplied by the speed of light squared. This means that even tiny amounts of mass require extreme energy requirements to create matter. This has been done in labs, but only with particles on the subatomic scale.
We're imagining something far greater here. If Antman was going to become 100 times his height, then according to the square cube law, he would become 10 million times his weight. Taking the previous weight of 86 kilograms and scaling it up accordingly, to generate that amount of mass would require 7.73 times 10 to the 24 joules of energy.
For reference, this is about 10,000 times more energy than the Earth uses every year, or about 1% of the energy the Sun releases each second. So, all you'd need to pull something like this off is a way to harness the complete power of the Sun. Nothing too difficult then.
Now you may remember we said first problem a moment ago. There's a second, somehow larger issue. Matter is not produced in isolation. Whenever a particle is generated, it is in a pair with its corresponding antiparticle. Due to these particle-antiparticle pairs being oppositely charged, they attract each other and will collide and annihilate back into high-energy photons.
I'm sure you can see the problem here. Even if we were capable of harnessing the energy needed to create this extra mass, the matter and antimatter generated would rapidly annihilate, releasing all of that energy in an explosion never before seen on the face of the Earth. It wouldn't quite be enough to destroy the planet. The Earth's gravitational binding energy is a couple orders of magnitude greater, but it would certainly wipe all life from the planet. In this case, Antman would also die. Still, we've at least gotten to something that makes physically more sense, even if it's practically impossible, so small victories, I suppose.
Actually going back to the square-cube law that I mentioned a minute ago reveals a final issue with the idea of growing. I said before that growing to 100 times your height would cause your mass to increase by 10 million times. This is a problem because the materials that make up the human body were not designed to handle that kind of stress.
At that size, your body would collapse in on itself like a house of cards, muscles too heavy to even move themselves, and organs too massive to support their own weight. Even if you were to somehow get past all the other problems with trying to grow and actually were to pull it off, Antman would still die. Perhaps if we want to grow, we'll just have to stick to eating our veggies for now.